That was pretty strong arguments for Earth-like life, isn't it? So, but I think it's a good beginning to switch gears to non-Earth-like life and give the opportunity to multiple times mentioned Steve Benner, whom we've seen before also on the panel. And I will introduce him. He is the head of the Foundation for Applied Molecular Evolution, and he combines approaches of natural history and physical sciences. He led his lab to synthesize first large-scale DNA and redesign DNA and RNA. He's a hardcore biochemist, as I understand, and we look forward to your presentation.
Do I have a way of changing these slides? Yes, look at that.
Good.
Right. So we're obviously interested in finding a universal life detection scheme. And there's a theory, we have to avoid this earthocentricity that we've been talking about. And there's this theory that Darwinism is the only way that inanimate matter can self-organize to give the properties that we value in life. And by Darwinism, what we mean is replications with imperfections, where the imperfections themselves are replicable. And Darwinism actually adds an additional thing to this, that these imperfections, that is, the variation cannot be prospective. That is, these variations must be randomly disposed with respect to future fitness. Now, you got to keep in mind that humankind has partly escaped this constraint. Now, it depends on how you view engineering. It's quite possible that, copper smelting was by accident when somebody put green rock into a campfire and then by accident scooped some cassiterite out of the shrimp. And even modern engineering, right? No one thinks that the 747 airplane is designed by random chance, but there's a large amount of random variation, like in drug discovery and other forms of engineering. What you do have to understand is that this germline genetic engineering, you will escape the biological constraint, but not necessarily the engineering constraint, because we don't really know what nucleotides we want to change in your inherited material to make you more fit in the future. But never mind. There are a bunch of ways of approaching this, and we've already mentioned some of them. So, for example, one of them is that this idea is that you could go back into modern biosphere and try to understand, as the one example of life that you have, what is the essence of that and try to look for it. And of course, you can go backwards in time and resurrect ancient and more ancient forms of life and to see how you would have detected that more ancient form of life. I won't talk about that right now. There's another approach which we have alluded to, and that there's an origins constraint. That is that you can say that, well, there are only a very few paths a limited number of paths to Darwinism by origins, and therefore maybe you need dry land, therefore it could not have occurred in some location which never had dry land. I won't talk about that either. I will mention that we are going to have in October in Georgia Tech, the Simons Foundation and the Templeton Foundation have jointly organized a program where we're going to be looking at that problem separately. But what I'm going to do today is instead talk about this sort of synthetic approach where one is going to try to make in the laboratory alternative forms of information so as to try to understand the constraints on what biology could have, and then go look based on that information that you get. Now, let me make the comment about replication with imperfections, where the imperfections are themselves replicable. So replication with imperfections is easy. So here's fire, which has a metabolism, it consumes fuel, it does all sorts of things, and it can have children, right? So a fire can jump, as it did in Santa Barbara or many other places in the California environment, and it does create a grandchild fire and then a grandchild fire. That replication is imperfect in its details. In fact, it's not the same as the mommy fire. But the grandchild fire does not capture the changes connecting the mommy fire or the grandparent fire to the child fire. Are you with me? So. And that's the same true with crystallization. For example, it's very easy to do replication in crystallization. You take a crystal. This is on the left is sodium chloride. It actually has a hand to it. There's a left-handed crystal and there's a right-handed crystal, which you can tell by whether they're more blue or more brown looking at polarized light. You can powder that crystal and you can sprinkle it throughout a saturated solution of sodium chloride and get more crystals. And you can even carry forward the handedness of the crystal from one to the next. Now, there are defects in those crystals. In fact, there's probably more defect in any one of these crystals in terms of information than the entire human genome. but there's no mechanism for having that imperfection carried through to the next generation. So it's getting this replication with imperfections that goes on to the next generation that's a problem. So I'm a big fan of this definition of self-sustained chemical systems capable of undergoing Darwinian evolution. I'm quoting now from the Europa report, who pointed out that Chiba said that, well, this is not a very good operational definition, even though it may be sufficiently broad so as to be universal. Because the question is, how long are we going to wait to determine whether the system we have in front of us is capable of Darwinian evolution? Well, the answer is you don't have to wait, right? The facts are, and by the way, Chiba is a brilliant guy, but you don't have to wait very long because one really does not need to recognize, to look at that rabbit and to understand that that rabbit itself is capable of Darwinian evolution by its structure. Now, I've got a small problem here, and that is that you are not putting up the slides that were the revised slides. You have the slides that were the original slides. So unfortunately, this talk is now going to go in a direction that I did not intend it to. Can you put up the file that has the word revised after it? And, oh, okay, I was going to continue to fake it, but maybe I won't. No, there was no defects up to that point. But at this point, I was going to then start to talk in great detail about the detailed structures of biomolecules that are involved. And I realized roughly at 10 o'clock this morning that this audience was not prepared for a detailed discussion of molecular structure. Is this the one that says revised? So if I go backwards, there you go. Brilliant. Okay. So that's excellent. Okay. So even there, I noticed that we have the notice of the so excellent. So why, you can ask the question, are replicable imperfections hard? And in a word, it's chemistry. And for those of you who don't know about chemistry, it's this quasi-science that lacks the rigor of physics and it lacks the interest of biology. It's the bane of pre-medical students. And it's the field that the American Chemical Society desperately promotes as the central science, right, for that reason. And there you are, and whose mascot is? Very good, a mole. A mole, but you can ask the mole is perhaps sufficient reason to explain why chemistry is so disrespected, okay? By the way, Dave Smith said that he wanted to have one picture that you would remember. The picture you're going to remember, and the point is that chemistry is important. It turns out to be quite critical. And let me see if I can tell you a little bit about this. In chemistry, most chemical systems, if you make a small change in the molecular arrangement, you generally have a large change in behavior. It's a very common phenomenon. So in computer A-life, for example, which you'll hear about a little bit later, systems that replicate with replicable errors are abundant because they're programmed, right? But in chemistry, in real chemistry, such systems are scarce. And that's true in proteins, in polysaccharides, synthetic polymers, all sorts of things. But let me just use one example, and that's hemoglobin. You change one lousy amino acid in hemoglobin at position 576, and the hemoglobin precipitates. And it precipitates and forms these sickle cells, which you see at the right, the red blood cells. So now sometimes in biology you want to have precipitated biomolecules, but you really never want it in your genetic molecule that's going to support Darwinism, because that really screws up the process by which you do replications. Now, that is, if DNA or RNA, for that matter, precipitated every time a nucleotide changed, evolution would grind to a halt. So a genetic biopolymer really must have fairly constant properties if it is to support Darwinism, where it is replicated with imperfections, where the imperfections are themselves replicable. And so pretty much every DNA RNA sequence dissolves in water. Pretty much everyone binds to its complement using these Watson-Crick rules. Pretty much every DNA RNA molecule precipitates in ethanol if you were to try it. Pretty much every DNA RNA sequence templates polymerase activity. So what is it about the structure of DNA and RNA that is different from proteins? Well, proteins have a repeating dipole in the backbone, and DNA, RNA have a repeating monopole, that is a repeating charge in the backbone. So there's the backbone repeating charge, there's the cartoon structure of DNA. And so we can compare this, right, with a repeating dipole. And I brought an example here. This is, we're not looking for the elusive physics monopole, but this is a magnetic pole. This is a charged dipole. But what happens when you have a bunch of dipoles on a string? Well, you bring them together, right? They collapse on each other. And then because they fold and because they fold intrinsically, it's hard to get them to template things. And of course, templating is the key association of replication. But with a repeating monopole, right, that doesn't happen. The repeating monopole, that negative charge, negative charge, negative charge, negative charge, negative charge, negative charge, negative charge in the backbone of the nucleic acid causes that molecule to stretch out. It prevents it from folding on itself to a large extent, and by the way, as a result, it keeps itself dissolved in water. So unlike the egg that you had this morning, where the protein intrinsically precipitates even though it starts off as a soluble egg white or egg yolk, this proteins will intrinsically precipitate just like those magnets on a string will interact with each other. Now, we make the argument that the repeating monopole is the only way to get replication with errors without destroying the properties to allow the errors to be replicated. And the reason why we say that is because we've tried to do it differently. And I've just put a bunch of other alternative structures on this folder where we have different things connecting two bases, right? Every one of those is a graduate student dissertation in my lab or in somebody else's lab with many tiers when it turns out that these things don't do molecular recognition like DNA or RNA because they don't have this repeating charge in the backbone. They fold. In fact, some of them even catalyze reactions. So why Darwinian polymers in water need a polyelectrolyte backbone? Well, first, it keeps them dissolved in water. Second, these backbone Coulombic repulsion forces strand-strand contacts to the Watson-Crick edges of these bases, which is how you actually get these Watson-Crick rules, A pairs with T and G pairs with C. If you don't have those repeating charges, you don't get those binding rules. The repeated charge discourages folding, as I've already mentioned, and the repeating charge, however, most important, dominates the molecular properties, allowing mutation to occur without changing the bulk properties of the water, of the biopolymer. And so this is the so-called polyelectrolyte theory of the gene that is universally, all genetic molecules, anything that supports Darwinism has to have a repeating charge in the backbone. And by the way, it can also be a positive charge. So it turns out that this property capable of surviving mutation independent of concern of loss of properties essential for replication has a useful acronym, cosmic LOPER, and it's actually a more fundamental universal property than another one that was proposed by Erwin Schrödinger, actually in the 1940s, and he argued that the universal genetic polymer must have an aperiodic crystal structure in order to have highly faithful replication. Now, Schrödinger did not know the structure of DNA, but he did know about phase transitions in physics and understand how important that was for having a sharp discrimination. Well, it's like why a crystal excludes impurities, for example. Very important. And so the idea is that a universal Darwinian molecule now must have two properties. One property is that it must be able to mutate without dramatically changing its properties. That's a very rare thing in chemistry, and it's achieved by DNA and RNA by having this repeating charge being the most important molecule feature, a feature that so dominates the behavior of the molecule that you can change A to G or C to T in the backbone without changing the physical properties of the molecule. And the second thing is that when you do change A to T and C to G, you've got to be able to have that change go without disrupting greatly the structure of the molecule. That change, it still has to fit into the same aperiodic crystal structure, which means, among other things, that if you have a chiral molecule, all of the building blocks in that biopolymer must have the same chirality. They must have the same hand. Okay, so are you with me? Two criteria for the universal genetic biopolymer. It's got to be, in water, I keep emphasizing this, it's got to have a one-dimensional polyelectrolyte structure, can change its structure without change its information content without changing its physical behavior dramatically, where the change units fit into an aperiodic crystal structure, same size, same chirality. So that's what we have to look for when we're going to go look for molecules. By the way, the rest of the DNA is not universal. There's the cartoon structure of the DNA that you know of, A pairing with T and C pairing with G, but there's the structures in Lego form on the left and the structures in molecular form on the right. But it's entirely possible now to go back and change, make Lego structures of all other forms of prongs and holes. And we've actually synthesized all these, and we've actually can show that they can do Darwinian evolution. And you're looking here at the evolution of a 6-letter genetic alphabet to perform a function. In this case, is the cleavage of RNA. Okay, so that's cool. So we're looking for a one-dimensional polyelectrolyte biopolymer with building blocks that fit into an aperiodic crystal, and that's the universal search structure for life. Now, it turns out that you have a win here, because if I got a polyelectrolyte with a lot of negative charges on it, it is very easy to recover that out of dilute solution just by having a capture element which has a lot of positive charges on it. And of course, if the polyelectrolyte has a lot of positive charges on it, I can capture that by a surface that has a lot of negative charges on it. And so polycations will bind to a polyanionic surface much better than monocations, and polyanions will bind to a polycationic surface much better than monoanions. I think I said that right. So if you got a sample of Enceladus or Europa, you flow it over a polycharged surface, you'll collect all the biopolymers that are capable of Darwinism, and then concentrate them at your leisure, no matter how infinitely dilute, well, indefinitely dilute, they cannot be infinitely dilute. No matter how much you can capture, you can then go back and at your leisure determine whether they fit Schrodinger's criterion, which is to make sure, well, you can detect them as by virtue of the capture. I've just produced one of these notional devices that detects the binding by displacing, well, it detects the binding in this case of a polyanion by displacing a fluorescently marked polyanion. This is a technical detail as to how you would see this. But the idea is that once you have captured, collected the polyelectrolytes, you can test their building blocks to see if they meet the Schrodinger criterion of being able to all fit into the same aperiodic crystal structure. How are we doing? So that's cool. So the strategy is simple, right? Similar size, similar homochirality is the Schrodinger criterion. It's universal for any life form in water. It assumes only the universality of Darwinism and the polyelectrolyte theory of the gene with linear information. Of course, now we've got to ask about weirder life, which would be of two things. Perhaps we don't have a unidimensional information. We have a two-dimensional information. That's kind of weird. Or maybe you're working in a solvent other than water. And we've heard a lot about them. So there's Europa and Jupiter in the background. What's the biggest, most important solvent that you see? Well, it's not the water that's coming out of the hypothetical plume in Europa, but it's the supercritical dihydrogen helium in the Jupiter behind you. A lot more volume, right? So and here you have Saturn and Titan. Of course, there's a lot of supercritical or dihydrogen helium, presumably in Saturn as well. This side of it, you see Titan, which of course has these methane oceans at 95 Kelvin, which you've heard about already. So you can go looking for life, for example, on those oceans on Titan. Now, polyelectrolytes actually don't work in methane or any of its higher hydrocarbon homologs. As you well know, oil and water do not mix. A polycharged species doesn't even get a chance to dissolve in oil. It's a water molecule. And even dipos don't work well in oil. They aggregate and they precipitate. So the idea was very simple. Okay, you're going to go back and try to synthesize now a molecule that might do the same kind of cosmic Loper behavior in oil that is needed for Darwinism. And so the idea was that maybe we should synthesize a molecule where we put one end of the dipole always inside, tucked away from the molecule, and the other end of the dipole is always presenting itself to the solvent. So this is what we have in these structures of polyethers, and the idea is that by burying one end of each dipole and exposing the other, the polymer might avoid aggregation and precipitation with delta plus, delta minus interactions, and maybe this will allow replication with error, not precipitation, allowing the errors themselves to be replicable. And so, well, okay, so I mean, I must say that we've made these molecules, and one of the problems that we then did was went back and tried to get them to dissolve in hydrocarbon solvents. Methane boils at 112 Kelvin at 1 atmosphere pressure, so it's a little hard to handle. These are actually done in propane, and you have reasonably good solubility at 190 Kelvin, which is, by the way, cold from your perspective. But by the time you get down to 150 Kelvin, and certainly well before you get down to 95 Kelvin, the amount of solubility of these molecules is 1 molecule per ocean, and it's really not a good thing to do. Well, this reminded us of a remark, oh, by the way, of a remark that William Baines made. You've already heard of his mention today. That water is a good solvent because it's hot, okay? It just is all there is to it. There's a whole bunch of other organic solvents that we use in organic chemistry. I mean, dichloromethane would be a wonderful solvent. A lot of people work with it. That blue is the blue wedge in this pie chart, which shows you that lots and lots and lots of organic chemists use dichloromethane as their solvent. Other solvents are available. I mean, supercritical dihydrogen helium is a wonderfully abundant solvent on this solar system, but you'd be amazed at how little literature there is on this material. And there's a reason for that. But never mind. So nevertheless, we do believe still that dissolution is needed for metabolism. This is chemistry lab rule 1. So you can look for other solvents. These are actually, we've picked up from William Baines' material talking about alternative solvents in which you can try to get hotter things like ammonia, especially if you put it under pressure. Of course, once you go to supercriticality, the game changes. As you all know, your coffee is decaffeinated with supercritical CO2, and this is a different solvent system which is not very well explored. So, and then there's some more work. So what should you remember from this talk? That is, if Darwinism is a universal requirement for biology and water, there are two universal constraints on any linear biopolymer to support it. The first is the cosmic Loper criterion. This polymer has to have stable physical properties with respect to informational change in structure. The second is the Schrödinger aperiodic crystal criterion. That is, they have to all fit. We argue elsewhere that this is the only way to definitively seek Darwinism. Now, I don't argue that today because the fight would go well into the evening. But the idea here is that it's directly useful because that biopolymer polyelectrolyte is directly capturable even from very high dilution solutions. And the reason why we have some confidence in these statements is because of the synthetic chemistry where we synthesize lots and lots of alternatives to come up with these rules. We have synthesized alternative polymers with more letters that support Darwinism, and that is on the way to a synthetic Darwinism that is not related by common ancestry to anyone in this room. What's wrong with that is a mechanism for discovery. It's like looking at a painting by Picasso. True, it's a woman that is not related by common ancestry to every woman that you know, but it tells you more about the artist than it tells you about the woman or womanhood in general. And that's what's wrong with it. The molecules that we make, which are unnatural, which support Darwinism, indeed, they are a separate origin, but they're telling you more about us, the designer, than they are telling you about life. But the second point is that we have really failed to synthesize a polymer that might support Darwinism in methane. That might tell you more about us than it tells you about methane, but the bottom line is that it might be working in a warmer Titan. So if you get an exoplanet, which is rocky, higher molecular mass gravitational pull greater than what we have on Earth, closer to the sun, and it has hexane, octane as a solvent, this might be useful. So these statements all guide our search for normal and weird life in a self-sustaining chemical system capable of Darwinian evolution. Well, with that, let me stop. Thank you for your attention on this. But the point here is that synthesis is important. There's a whole separate thing. And anybody who wants to come to this thing at Georgia Tech in October 15th should give me a ring. Thanks much.